All right. So for this example, we're going to see the effect of adding or increasing the ionic strength to the solubility of insoluble salts. So in this question, we have AgCl, which is an insoluble solid, meaning that when you try to dissolve it in water, only really small amount of it will dissociate and form silver ions and chloride ions, right? So where do I know this from? I know this from the Ksp value, which is quite low, 1.8 times 10 minus 10. Now the Ksp, if you remember your previous material, so it's a function of the concentration of the product over the concentration of the reactant. So the reactant here is a solid, so we consider always as 1, and we only care about the concentration of these ions. But now in chemistry 311, we discuss in terms of activity. So the Ksp would be a function of activity of silver ion times the activity of chloride ions over the activity of the solid, right? And the activity of the solid is 1. So the activity is a function of concentration times the activity mean activity coefficient for both for silver ion and chloride ions. So because this is a one-to-one system, so for every molecule of AgCl that dissolve or dissociate, you will have one ion of silver and one ion of chloride. So then in principle the concentration of silver is equal to the concentration of chloride, right? Okay. Now the question is what is the change or the increase in solubility of AgCl? That's here. That's the M, or in some books they use S. When an additional salt is added. So when you add sodium nitrate here, 0.1 sodium nitrate, which has not participating in this reaction. There is no sodium, there is no nitrate in this equation, in this chemical equation. But because these large amount of ions that were added to the system will increase the ionic strength, it will change the interaction, the ion-ion interaction. Now let's compare two cases. First, when silver chloride is dissolved or put in until equilibrium in pure water. So if this is the central ion, meaning the silver ion, it would have a large sphere, because if we assume gamma to be close to 1, so with the Ksp equals to m square gamma square equals to 10 minus 10, and because this is 1, so m would be equal to the square root of 1.8 times 10 minus 10. So this is equal to 1.34 times 10 minus 5 molar, right? So this is so in pure water, when we assume the gamma equals to 1, the concentration of the ions of silver is 1.34 10 minus 5 molar, and also chloride the same, because it's 1-to-1 electrolyte, 1.34 times 10 minus 5 molar. And the ionic strength here of the case in the pure water will also be the same for 1-to-1 system. Yeah. Okay. So if I can write or describe it into in a sphere, right? You will have really low ionic strength. As a consequence, then the sphere will become really large, right? Because or the 1 over kappa, the Debye-Hudson screening length, will become really large because kappa is small. Now the question is, what happens if you add in 0.1 sodium nitrate, right? The sodium nitrate here, it would dissociate into sodium ion plus nitrate ion, and it will occupy the electrolyte, and as a consequence the ionic strength will increase. Now how to calculate the ionic strength is just simply, because this is 1-to-1 electrolyte, so the ionic strength is the same as 0.1 molar. So if you compare, when we add 0.1 sodium nitrate, the ionic strength will be 0.1 molar. When there's only pure water, the ionic strength would be 1.34 times 10 minus 5. That's 10,000 times higher the ionic strength when you add in 0.1 sodium nitrate. Right. So then you can imagine that the sphere now becomes much smaller once 0.1 sodium nitrate is added. Right. So there will be significant ion-ion interaction. So that would change the gamma, mean activity coefficient. Now we have to calculate then gamma, because gamma now will no longer be close to 1. So we have to calculate gamma according to the Debye-Huckel equation. And I. So here Z plus is 1, Z minus is minus 1, so this is put in the absolute value, and square root of 0.1. And this will give us a gamma about 0.6897, right? So now we have a new gamma. So in pure water we assume that gamma is about 1. Now in the presence of 0.1 sodium nitrate, we have gamma 0.6897. That's about 31% drop, right? So now what do? We go back to this equation where we calculate the KSP is equal to the activity of silver plus and the activity of chloride minus. And we are interested now to find the new M, right? Because in the case of pure water, when we assume gamma is 1, we found the M is 1.34. Now with much more ions in the solution, or higher ionic strength, we have lower gamma. Okay. And then we have to calculate. One thing to remember is that the KSP, or equilibrium constant, does not change with adding ions. So the KSP remains the same, right? But in this case, what changes the ion-ion interaction that manifested in gamma, right? So the KSP does not change, right? It does not change with adding ions. So we have 1.8 times 10 minus 10. We don't know the solubility yet. We have to calculate that, but we know from the Debye-Huckel limiting law that gamma is 0.6897. We square that, and solving this, we get M to be equal to 1.94 times 10 to the power of minus 5 molar. Now let's compare this value with the case of the pure water. So with adding a lot of ions, the solubility increases. Where mathematically we can understand this, because as we increase the number of ions, increase the ionic strength, gamma will decrease, and when gamma decrease, the solubility, or M here, will need to increase in order to keep the equilibrium constant the same or constant, right? So there you go. So now we have the new value of solubility when you have 0.1 sodium nitrate, and compare that to when it's in pure water. So the difference between these, the difference would be 1.94 minus 1.34 over 1.34 times 100%. That would be around 45%, right? So by having more ions in the solution, you increase the solubility of AgCl by 45%.